In this video, we're going to use our Schlieren optics setup to try to visualize sound waves traveling through the air. Now, they move really, really fast. In fact, a sound wave would take less than 1,000th of a second to go from one side of the mirror to the other, and that's way too fast to see. So we're going to use the stroboscopic effect to try to freeze these waves or give us the illusion that they're frozen in space. You've probably seen this kind of effect before, especially if you've used a stroboscope. Like if you have a rapidly spinning wheel, if you flash a bright light on it, every time it makes exactly one revolution and it's off the rest of the time, then it gives the appearance that it's just motionless because you see it in that same position every time. So we're going to do something very similar in this setup. The transducer here is producing sound waves, and every time it produces a wave, we're going to flash a light on for just a few microseconds, and that will effectively freeze that wave in space. But you're not going to see just one wave frozen in space because this thing produces 28,000 waves every second. So you will see a whole series of them frozen in space. So let's have a look. All right, I'm going to turn on the sound waves, the transducer, and I'm going to wear hearing protection even though I can't hear the sound. So there you see the waves frozen in space. I've also taken this ruler and put tape marks on it every 1.2 centimeters. I'm going to hold that up to the transducer, and you can see that the distance between the waves, which is the wavelength, is 1.2 centimeters. So knowing the wavelength, knowing that it's 28,000 waves per second, you can calculate the speed of these waves. Now, since we're trying to visualize waves traveling through space, we don't really want to see them frozen. So let me turn on the transducer again. What we'd like to do, or what I'd like to see, is them traveling forward in space. And we can make that happen by strobing the light at a frequency that's a little bit less than the frequency of the waves being produced. In doing so, what's going to happen is that every time the light comes on, because it's a little bit slower than the wave will have progressed forward in space just a tiny bit. So it'll give the illusion that the wave is moving forward. So Alan is going to adjust the frequency of the strobe just to be a few hertz less than the actual frequency of the waves, and you can see that this gives us the illusion that they're actually progressing forward in space, which is kind of the way we like to see waves going. If, on the other hand, Alan adjusts the strobe frequency to be a little bit greater than the frequency of the waves, then the wave will not have traveled quite as far as every time that the light comes on. And that gives the illusion that it's actually moving backwards, which is absolutely not happening. It's just an illusion. So Alan is going to adjust it so that the waves look like they're progressing forward. Seeing the waves move forward, we can now show you some of the characteristics that are common to all waves. Here's a piece of plastic, which I'm going to use as a reflector and put it into the path of these traveling waves. And you can see the waves are reflected upward. For example, if I move the reflector in the other position, I can reflect them downward. I can reflect them downward so that they bounce off of the base of the mirror and back up again. And if I set this reflector down, you will see that the waves also bend around this barrier. They bend around and actually go into the shadow of the barrier, and this is what we call edge diffraction.